this will actually go into our Google Drive. So anyways, going back to the vertical scaling versus horizontal scaling.
Law.
So so vertical scaling, i.e. individual human being, we're reaching asymptotic limits, whereas your horizontal scaling, networking with other computers, networking with other humans, that starts following Metcalfe's law. And then in my line of business, we have this thing called the service mesh. How do you ensure, like you have a bunch of microservices, how do you determine which microservice can talk to another one? What are the security, the networking policies that you apply to it? And it's interesting how that, whether the inventor of that concept looked at human societies and kind of invented that concept, there's a lot of similarities between that concept and how do you govern a network versus how do you govern a human society, right? If a node is misbehaving, you don't want to have other nodes keep on talking to you. You want to isolate often itself, right? In this case, it's like putting someone in jail if a person stops cooperating.
Quarantine of data coming in and out, and you have to examine what's happening in there.
Right. And then the security protocol between these nodes based on the mutual trust. Right, you have to trust, you have to establish trust with another node before you're communicating with it, because you don't know what it's actually all about. And hence, in human societies, you have these, we have high trust society, and we have the social cultural norms and everything. These are all, if you think about it, these are all forms of protocol. In fact, the word protocol came from that sense before computer protocol, networking protocol was even a thing.
Right.
It's as simple as when you meet someone new, you go shake hands with them, because if your hands are in front of you, you can't be holding a dagger. I think that's where it came from.
That makes sense. Yeah, I think of Christianity really as a set of surviving protocols from the Roman Empire that, for whatever the subversiveness of early Christianity, the Nash equilibrium amongst people in Europe settled on Christianity, the mythology, because if you could quote this story about an innocent man going through a horrible death on cue, you're probably an empathetic person and won't pull a knife on somebody else, you know? So essentially, yeah, in other words, the ability to test someone's memory of the basic stories of Jesus could kind of like protocol verify, does this person grasp the moral teachings of Christianity, or are they an idiot and they only believe in the miracles of Christ, like, you know, walking on water and like that's what. So it's like the mind of a 5-year-old, right? Like my son is 4 and he thinks, you know, extra physics is just like the craziest thing. But by the time you're Evelyn's age, like, you know, no, it's like, yeah, I know that's not real.
No, Santa's not real, and there's no tooth fairy.
There's no tooth fairy. Like, yeah. So let's not ruin it for all those people who still don't know. But yeah, so I think the protocols you're looking at in regards to networks. When you have networks operating together with networks, their interfacing involves protocols and all these different microservices. That's what you were saying. So you wind up with just the mathematics of it all is just networks, essentially. And back to, you know, Ted Kaczynski's power process. It's like, you know, technology may have stopped some people from. I would say technology, and then the concentration of humans in a civilized built environment, which he tried to escape in Montana, certainly, you know, impedes a man's power process, but so do other humans. Other humans always like have impeded each other's power process. And then Metcalfe's law, I think what you're bringing that up is to say that if we can channel our energy into networking with one another or federating properly along the right micro protocols, you wind up getting a Metcalfe's law, or, you know, where the number of people in the network squared becomes the strength of the network against other networks.
Yes.
So that was kind of the big picture, I think, of what you were trying to illustrate there.
And to that effect, it's not about an individual human's power process, but the entire species power process. Because we know, or I mean, I guess we deterministically know that there's a high probability if we keep on staying on this Earth, eventually we're going to die on this Earth as a species.
Yes.
And so we have to achieve enough power as a species to go.
Yes. Escape velocity.
Exactly. Escape velocity to spread the seed across the galaxy.
Yeah. We have to be able to, we have to be able to, I don't even think colonizing another planet is really where it's at. I mean, that's part of it, but can we just build a capsule and go live in it out in space? You know?
In a self-sustained manner, if we can solve the energy problem.
If we can solve the energy problem, yeah.
Right, but then if you can solve energy problem in an inhospitable place in space, you might as well solve the energy problem here on Earth.
That's right.
So I don't think it's either or. It's really, don't put all your eggs in one basket in this place called Earth. You may want to divest and put your eggs in other baskets.
Yeah, for sure. Yeah, I mean, my kids' kids might be astronauts, you know, and part of the colony on Mars, or certainly part of the terraforming of it.
Yeah. Anyway, shall we go to the main topic?
This is a really great segue into the game analysis, because when you were mentioning,
share the picture.
Oh yeah, thanks. The picture.
Okay, so I only had the time to briefly look at this. But just tell me what the columns mean. So you have continuous space. That's a first column. Discrete space.
These are the four domains of mathematics that sequenced that I can sequence in this list according to the number of dimensions of the system.
Okay.
So the continuous space, which we just think of as like the X and the Y axis, or maybe X, Y, and Z axis, a Desmos graphing calculator, Newtonian physics, all of calculus and like higher level calculus and topology lives, continuous topology lives in this space. And discrete space, the next column, concerns now more Curt's realm, where we don't allow there to be a continuum of states to exist.
Oh, I see. So continuous space is really cardinal, and then discrete space is ordinal.
I should have written that. I forgot to write that.
Yeah,
Thank you.
The discrete space, you just have order. You don't. Your distance between two position names are not constant. In fact, they may not even be quantifiable.
Yes.
Yes. But why is fractal in here?
Fractal because a fractal concerns, I think the technical definition of a fractal is that if you take any image and then you kind of divide that image up into tiny graph paper, and you make a measurement of the ratio of the let's say you're trying to measure the coastline of England. That's like the classic example that's been in a whole bunch of videos
it's
online.
Self-similar. You can zoom in almost infinitely, and then at some point, the beach looks like it takes a certain similarity to the shape of the coast of England.
The thing is that the fractal is always measured through a discrete process. There are no fractals that we can actually calculate continuously, if that makes sense. Like to do the Mandelbrot set, to calculate that, we have to run a simulation, a lot of steps, 20 or 30 or 40 steps, to know how to move from neighboring point to neighboring point. There isn't just some handy dandy rule that lets you travel from neighboring point to neighboring point. It's a discrete space, not a continuous space. And that's why when you can keep zooming.
Does this mean, sorry for interrupting.
That's okay. No, interrupt anytime.
In continuous space, you can use math to project the future state, such as 1 + 1 = 2, right? A future position. Whereas in discrete space, in the fractal sense, you can't just add, say, arithmetically add two numbers in a fractal and arrive at what the eventual thing is going to look like. Here in column 2 for fractal, you actually have to engage in computation.
You actually can shortcut it. There are many calculations also in the discrete space, but is there a way to write on this? I'm just trying to.
Not in this thing, but there is a whiteboard.
How about I'll create a quick
whiteboard. I just created one.
Oh, perfect.
And share it with Michael as an editor. It should be coming up. Okay, it's here. It's a board. I'm just going to drop it in the.
Oh, here it is.
Yeah, it's already in there.
All right, so I can draw them. So,
yeah.
So in the continuous space, the basic idea is that if you were to look at your graph paper.
Let me present this so that. Entire screen. There we go.
Oh, this is fun. Yeah, this is nice.
Oh. And it'll also show up in the recordings.
Oh, great. So this point, which has no size whatsoever, that's in the continuous realm, moves through the space, and between any 2 points, however close they are together, it is guaranteed that there is an infinity of points between those 2 points. Yeah. So that's
the continuum.
Exactly. That's the continuum. Whereas in the discrete, it's like really what you see is what you get. So in the case of the discrete, even if you want to, you don't necessarily have to draw it on graph paper, but if you did, that same curve would like only make sense, like this. Sorry, I'm not drawing it very well, but it would be moving in particular arrows. Like, so the discrete space, everything shifts to points and arrows between those points in the discrete space. So like the discrete triangle.
So despite the lines connecting the points, there are really no positions between them.
That's right. That's right. The discrete space is the measurable space. In other words, we can measure that there is a location, and we can measure a motion between 2 locations. But in the continuous space, this is one continuous solid geometric object, whereas here we have A, B, and C. And, here you can travel any number of points between A and B. Whereas these blue arrows mean that there's not really an in-between state. This blue arrow, in other words, is a function.
Right.
This is actually
it's a state transition.
That's right. So this is a function, F1, this is a function, F2, transition 2, this is F3. So whereas, here there's a real numbers worth of states, and, here there's a real numbers worth of states, and here there's a real numbers worth of states.
And therefore it is not measurable because you cannot measure infinity.
Yeah, you can have all sorts of pathological things in the continuous space that you can't have in the discrete space. So I'll give you one example. This is I'm sorry that this is such a pedantic example, but we're just going to look at what's called the Dirichlet function.
Okay. I don't know it.
Yeah, no, it's okay. Basically, the idea is in the Dirichlet function, you add up the area under the curve that's defined in the following way. F of that, let's see if I can write it. I'm still getting used to the writing here. Here we go. F of x equals 1 if x is rational, and f of x equals 0 if x is irrational. So this gets right into the Curt's Cantorial kind of counter argument. If Cantor's continuum exists, or Cantor's version of the continuum exists, you can define a function like this, and you can try to take the area under that function from, let's say, 0 to 1. And the idea is that there's an infinite number of dots up here at 1 and an infinite number of dots down here at 0. But it turns out in math terms that because there are so many more irrational numbers than there are rational numbers. In other words, the density of the irrational numbers is just so much higher than the density of the rational numbers that the area under the curve is essentially 0. And that's a math result. That is true in the continuum. In the discrete, you can't have irrational numbers. Or if you do have irrational numbers, they are themselves discrete states that are just locations that you can be at. And there's no in between, or there's no like philosophical argument. It's just you're there or you're not.
Sorry, take one step back. Is when I learned rational numbers, irrational numbers, I was in China and they go by a different name. So rational numbers means that it can be turned into a fraction. And irrational numbers are things like pi and what's another number?
Like a square root of 2 or e.
Right. So basically the decimals keeps on going, but they never repeat.
That's right.
Okay. So the ones that do repeat, like 3, 3, 3, 3, like when you divide 1 by 3, is that a rational number or irrational number?
That's a rational number because the repeating just means, in other words, rational numbers have stable terminating algorithms. So 3/10, for example, can be thought of as 3.30 repeating, and we normally don't think of the O repeating as any big deal.
Oh, I see.
So by the same logic, we shouldn't think of repeating 3 as a big deal either. It just means we have the wrong base. In other words, we're in base 10 and we're trying to calculate something that's a base 3. So of course we're going to get an infinite sequence, but the sequence never terminates. 1/7, I think, is like 0.1142587, I think, repeating.
And it keeps on repeating.
And then it just keeps repeating. And but like, here's a weird one. Like, look at this number: 0.010010000100. You know, it's like there's a pattern, obviously, but this would be called an irrational number. And in fact, it's known as
because you cannot reduce. I mean, algorithmically, it's pretty obvious. You can see that as an algorithm, but you can't. I guess I have no way of deducing that down to a what do you call it? A fraction, other than maybe writing a function to produce that number.
That's right. The key thing about fractions is that they're pairs. And when mathematics mathematics is very good at theorems about pairing things. Let's just say like
fractions of pair, you mean the numerator and denominator.
Exactly. In other words, if you wanted to create a system for keeping track of what a fraction is, you simply define the fraction A over B. This is sort of like number theory, how it's defined. It's defined as the tuple A comma B, and where A over B plus C over D, the operation of addition between the fractions can just be defined as follows, right? It's AD plus BC over what's it called? BD. And so then that gets turned back as an ordered pair into AD plus BC and then BD. So in other words, I want to try to get to another page if that's okay.
Yeah, I think you just click on the, so at the top there's there's those two buttons. I mean, there's that square thingy, and then there's also a next frame.
Okay, I'm on slide 2 now.
Yeah, there we go.
So like, in other words, the operation of addition, right? If you're going to define it as an ordered pair, the idea is that A comma B, the core property of A comma B is that A comma B is really always equivalent to B comma A. So if you're, in other words, if you're looking at an additive structure, if it doesn't matter which order in which you are in the ordered pair, then essentially you have something that is isomorphic to addition. So addition in like this is just like when I say number here, that means just like the world in which we normally grow up. So this is just convention, conventional math, like what everybody knows. Whereas this is the ordered pair construction, or the set theory. This is really a set theory construction of addition.
So let's do one more example. A minus B, that does not equal to B minus A. So then when you deduce it down to when you transform it into the pair set theory, what does that look like?
Awesome. Yeah. So in the case of A minus B, here's the idea that I've seen it, how it's described, and I'll have to write a little bit more down. The core idea is that if you have A minus B, and then you add that to C minus D, then I think then that means that you can go from the first ordered pair, which is, this is the ordered pair A minus B, and then the operation of addition on the ordered pairs winds up operating just like vectors does. In other words, we add the A's, so in other words, this is the ledger always of what you have, and this is the ledger of always what you owe. So the negative numbers from a set theory perspective comes into being from this construction. I'm gonna get my headphones because we're in a rainstorm now. It's kind of cool. Okay. I'll hit the dots thing. Oops. I guess I'm just wondering, how do I, from within of the web browser, change my... Actually, can you hear me fine?
Yeah, I can hear you fine.
I'm not worried about it then. I'm used to it. So anyway, so this would be the set theoretic structuring of subtraction, I believe. And I might have like a minor like quirk or detail wrong here, but I don't think I do. So in other words, if you have, oh, and then you can create an if structure. So basically, and then if and only if A is greater than B, right, and C is greater than D, then the result that you actually get is simply what we would call in common sense parlance, A plus C minus B minus D. But if not, you have to keep it in the ordered pair form, or invent a symbol called a negative sign, which reverses reverses the index on the ordered pair. So then it converts the second coordinate to the first and the first coordinate to the second. So that's what a negative sign effectively does as a multiplication.
I see.
So
the
this
negative is really there to reverse the half and the O.
The negative is there to reverse the direction of the subtraction. The identity is that A minus B is always the same as, mathematically, the negative of B minus A. And, you know, when you see it as numbers like 4 minus 5, therefore becomes the negative of 5 minus 4. 5 minus 4 is 1. So the answer would be negative 1. So that's how you instantiate subtraction. And I think this is also important. If you don't mind, I want to do 2 more of these.
Please.
I want to do fractions. A over B. So it's a little more complicated. Instead of an ordered pair, you need an ordered tuple. You need 4, or quadruple. You need, when you have A over B plus C over D, this gets kind of heady, but you're going to have A comma B is the first fraction, and then comma C comma D. And then within this like double set construction, you can then refer to the rules up here and the rules in here in order to add and subtract fractions, basically. So fractions requires now a pair of pairs. But if you are allowed to have a set, a collection of objects or stones, and you're allowed to have pairs of those things, then we're allowed to have rational numbers. We're allowed to have addition and subtraction of those rational numbers. So therefore, we have all 4 calculator operations totally ready to go as a set of ordered pairs, including some very special ordered pairs, like this one, 1 divided by 0, comma, 3 divided by 0. Now, this doesn't make sense as an actual number. This is a non-number. Do you understand what I mean here?
Of course.
So if I can go back here, I'm sorry, if I can go back here, the idea is that going from the number world has less cases than the set theory world. Seeing things in terms of sets, and then in terms of constructions of sets or sets of sets, if that makes sense.
I can understand that.
Allows you to, what's that?
So I can understand that. With a set theory, you can construct a lot more states than you can possibly do so in real numbers.
In the natural world. Yeah. Because this is an unnatural, this is an unnatural state. Unless it's literally just describing its own state as a bunch of stones and buckets. 4 buckets.
Okay, so going back to the...
Let's go back to that. Yeah,
let's go back to the first one. The continuous, the discrete space. And all right, so that's discrete. So then going back to fractals.
Yeah.
You said something about fractals. What is that you said? So am I correct to understand that for fractals, because for fractals, you can only reach these states through function, and there are no infinite... Actually, hold on, that doesn't make sense. Because in fractals, I'm just thinking of Mandelbrot set, right? In Mandelbrot set, you can infinitely zoom in, and it seems like every level, there's in between, and there seems to be infinite number. Actually, sorry,
the space is continuous. However, the updating for how you color that space is not a continuous function. I'll explain. In other words, in a continuous function, so let's say you have on a continuous function, you have 2 points. Okay, so you have we'll call this point A and point B. And then let's suppose that there is a color on each point. And we'll call that color C of A, which C is a function, and C of B. And we can kind of say that like C of A equals 0 would be like the color black in the Mandelbrot set. Whereas C of B, let's just say, might be 1, which would be the color white. And then there's like some sort of continuum of wavelengths between black and white. So we're going to say that this right here is, in fact, a continuous function. That's continuous. However, now if we look at the output of the Mandelbrot set, the output, here's a property of a continuous function. Bringing A and B closer together brings these 2 things closer together. That's the property of the continuum. If you bring A and B closer, then if this function is indeed continuous, then the outputs also have to be closer. So the inputs, if they get closer, then the outputs have to get closer.
And however, that's not true in Mandelbrot.
No, it's not, because you can find a border point that's black, and then if you zoom in, and then the next point in the pixel is green, but then you zoom in and that next pixel is not going to be green. It's going to be, in other words, it's going to jump all around, and it's not going to jump around continuously. You can't interpolate. In other words, on the Mandelbrot set, there's no interpolation possible, except when you know you're in a giant black region, or you know you're in a giant outside region. But at the borderline regions, the boundary regions, it's undecidable.
Ah,
That's the mathematically undecidable, is what are the colors at this particular zoom level? And that's decidable, that's computable. But if you want to then extrapolate or or really interpolate, either interpolate to two different points colors or extrapolate to what the colors are going to be in a whole region within the next zoom level, both fail. You have to run the algorithm all over again.
Yeah.
Only on the boundary. Only on the boundary. So save that thought. That's a very important thought that we'll use later when we reconstruct set theory in the ternary logic. My claim is that if you want to recover set theory with ternary logic, you have to treat the boundary as the undecidable state. So you're either in, which is the word true, or you're out, which is the word false, right? But then this boundary is itself
a state. The boundary is in itself a state, because otherwise you don't really have ternary logic. If the boundary is infinitely thin, then you either end up with true or false. You can't end up with undecided.
Yeah. So instead of an infinitely thin boundary, it's like a Mandelbrot set type boundary, where we have to add more context to be able to sort it out which way. Right. So every time you zoom in, therefore, on a particular boundary case.
Right, and you cannot interpolate between the in and out or true or false and to decide the boundary case.
That's right.
You really have to add more information.
That's right. That's my claim. I'm not claiming that is totally scienced yet. It's a claim. It's a way that could repair logic in the ternary logic case. Now, I'm going to make a counterclaim that the way that we really should be looking at it is through the idea of category theory. So we should actually go back to that picture.
Yeah, so that was what I was going to. Before we move on to the logic and the dimensional games, let's go to category.
Yeah, so category theory is gonna actually dovetail with both the discrete picture and games. You're gonna see that the three things on the three rightmost columns are actually somewhat similar, and then the column on the left, the continuum, that's the weird one. That's the matrix. That's the construct that allows us to get away with certain things very elegantly. So I'd rather teach kids calculus. Go ahead.
By cheating. Like
we're cheating.
In continuous space, you can in fact have infinity, right? Well, number of points 0, 1, and so on.
The real thing is that the continuous space is less complex potentially than the discrete space. That's the key. It's counterintuitive. You would think that because you have infinity allowed in continuous spaces, that you should have systems of more complexity, but in fact, it's only in the discrete realization of those things, like in the Mandelbrot set, that you get really trippy visuals and really interesting.
Define complexity in this context.
Like calculus is the least complex mathematics, because you can use this cheat code, which is that the cheat code is that any curved line can be thought of as an infinite collection of very small straight lines. That's the miracle of calculus. That's the rule. Any blob can be turned into rectangles. Any volume can be turned into squares or whatever, any shape you want, really. And so calculus lets you like the calculus and the real numbers are basically the same concept. They allow you to have an infinitely small denominator, or 2 points that are like infinitely close together, basically, which you can't do with the rational numbers. The rational numbers don't allow you to construct in other words, if you have a system that can only store 1 million decimal places, that's the finest level of resolution,
correct,
that you can operate with. Or if you want to store it as ordered pairs so that you can take advantage of bigger denominators, you still have a maximum storage of your denominator. Whereas with real numbers, the continuum of real numbers, you're allowed to find any point. You're allowed to take an infinity.
You're allowed to define something like 1/3 as an actual thing, whereas in reality you can never, because the decimals keeps on repeating, you can never you never have enough precision to really measure that state.
Yeah, exactly. 1/3 is expressible in stone pile as this, but like 1/2 is only expressible, in a geometric diagram side lengths, like 1/2, and this would in theory then be 1/√2. But whereas this pile, this stone conversion pile, right, of this per this is no longer easily expressible. Or I'm sorry, I should do a better triangle. I was kind of being stupid there. Someone's gonna be like, why didn't you just pick this? So I'll just do a slightly better one. So yeah, if you just take the basic 45, 45, 90 triangle, in theory, this length is the square root of 2, but that's only because we're asserting that this right angle is a perfect right angle. This is a perfect length of 1. That's a perfect length of 1. That's a perfect 45. That's a perfect 45. Both lines are infinitely straight.
Mm-hmm.
Someone can warrant that and measure that to infinite precision. That's the construct is what I mean. That's the continuum. So this relies upon our accuracy of construction to calculate, whereas there is zero inaccuracy in this 1 to 3. In other words, our data states will never be inaccurate in the rational number picture, but there is some inaccuracy introduced. There is some inaccuracy introduced in the case of the square root of 2. So even though infinity is kind of like the boogie concept, you can really, from a computational perspective, just define infinity as that there always exists a next iteration. There's no limit to the number of constructible states in one particular direction. That doesn't realize infinity. That still doesn't describe infinity as a set, but it does show that, like, amongst the sets that grow to infinity in size, there is a well-defined function that converts one set to the bigger set, to the bigger set, to the bigger set, to the bigger set. And that is actually at the heart of category theory, is the idea that there are nothing in mathematics other than there are states, which we use stones to describe, and there are functions or morphisms or maps, state changes between those states. So this is object A, that's object B, and this kind of looks just like geometry, or in the discrete picture. The only difference is that we are really clear that these things are functions,
But in the discrete space, to change between the states, you also rely on functions. So what's the difference here then between?
Well, the difference is that normally in the discrete space, the function is trivial, which is just you're traveling along the path in geometry space. Whereas this could be like the sine of x. This function could be like the sine of x, and this function h could be like the natural logarithm of x. In other words, we're now describing all the possible. The idea of category theory is that we're no longer really looking at states. We're looking at functions. We're interested. So let me just go to the next page and explain this. It's very simple, and then it gets very complicated. But in a category, you have objects, and objects typically are sets. And then we have also functions, or they call, in category theory is known as type theory in computer science. So a category
is like type, as in int, float, that kind of type, or
totally Boolean, double precision, single precision.
Right, a class, right?
Any data type, string, list, tree.
Yes.
Anything. The idea, however you want to type your system, because the idea is that there are functions that take objects of one type to the same type. So let's say, for example, you have an object that takes A to B, then you have another, or you have a function that takes A to B, then you have another function that takes B to C. I'm sorry, that function would be G, C would be down here. And I don't know, you have another function that takes A to C, and we'll call this H. Well, here's the idea in category theory. If you can prove that H is equal to FG, then this is basically a category. So the basic property here is called associativity. It's the associative law. So
Yeah, because if function h changes state of object A to C, and then you prove that by A through function f going to B, and then B
yes,
through function G going to C, they're essentially equivalent. Then what you're claiming, oh, so hold on, then are you claiming all these functions belong in the same category, or all these the objects A, B, C
yes,
belong to the same type?
everything, the objects and the functions are what make up the category. So the category is always an ordered pair of sets and functions.
Okay.
Yeah. And we have to make sure this, when I wrote this no here, we have to make sure that there's no other function that takes you from A to C. It's only H, and H is the composition. It's, in other words, it's the unique composition of F and G.
Why can't there be other functions?
Well, there can be, but if you have that, then you're no longer a category.
But why not?
Because you've lost what's called composition, the idea of composition of functions.
Oh, you mean there are no other functions that are different from H that can also get you from A to B?
That's exactly, to get you from A to C. That's exactly right. H is the unique function that takes you from A to C. And so the idea is that we now have we can establish that if you have two, this is going to get very geometric very fast. The idea is that if you can establish that you have two sides of a triangle, the question is there a unique third side?
Mm-hmm.
That's the core proof you have to make in all up and down category theory. So now what you're dealing with is you're dealing with types of, so let me give you some examples of categories. Matrices, square matrices are a category.
Well, I mean, the simplest one I can think of, right? When we talk about types and associate functions, the simplest way I could think of is in C++, you can have an int class. In int class, you can have the value itself, right? Which in this case will be the objects, and a set of operators.
In math, they call that int. In math, they call that int class or int type. They call that a ring.
A ring.
A ring. I have no idea why they call it a ring.
Is that an abbreviation?
Not even. No, it's not. It's the Germans. I don't know. But the basic idea that a ring is just basically a ring is a set that has addition, multiplication, and a unit.
Okay. And
then you can show that a ring is a type of category. A ring is a category. So in other words, ring operations, ring functions on rings preserve the laws of composition and or associativity. Meaning that anytime you encounter, if you want to get from like object A to object Z, the path that you take to go from A to Z, you're going to see this kind of triangle showing up all along that path in the category.
Mm-hmm.
So the idea is that category theory is concerned with theorems that come from these diagrams that are inevitable simply from the law of associativity or the law of function composition. So category theory has a way of categorizing all different types of math objects because it classifies their associative functions.
Yes.
Now, for non-associative things, they're not in the cool kids club. They don't get to be called a category. They could be called an allegory, which is simply a relation, the study of relations. But category theory has really been like the darling of, I'd say, the last 60 years of math in the theoretical end, because it organizes all the higher level theorems. Like when you realize Fermat's last theorem, the Poincare conjecture or whatever, pick your favorite theorem, is actually can be described as a theorem about two different categories. And there's this thing called a functor, which in computer science takes you from one type to another.
Oh yeah, cast, reinterpret cast or whatever cast.
Yeah.
But
so
the problem with cast, or at least the way when I was still programming, the problem with cast is oftentimes you can lose information when you cast things if they're not, especially if you're casting from a higher precision to a lower precision.
Yes. And so what you're just describing is that when you go from high precision to low precision in mathematics, in category theory, that terminology is known as what's called a forgetful functor.
Mm-hmm.
We call it forgetful. Or you could say it's not, in other words, it loses either a property, it loses a structure, or it loses stuff, which is just anything that we can't describe as a property or a structure.
I'll give you an example here, right? So let's say that you have two types. It's two classes. You have a class called cat, and you have a class called mammals. And cat is a gosh, what's the term? It's been too long.
Yeah, it's very academic.
Cat inherited from the class cat inherited from mammals. Now, mammals can walk, or there's something. Well, let's say mammals have fur, which is property, or mammals are warm, right? That's another property. And cat has this action called male. When you reinterpret cast a cat, an instance of a cat class down to mammals, you lose male, which is unique property.
That's right. So this is basically the minus meow functor.
Yeah.
For this. Oh, and a functor is a capital letter. So we use lowercase letters for functions, but for functors, we use capital letters, because a functor is a function between two categories.
Right. Okay. Makes sense.
Yeah. And so if, for instance, you take a ring, which is defined as a set with an operation of, there's an identity, there's an additive identity, and there's also a multiplication of some kind, but not necessarily a multiplicative identity. That's a ring. Rings don't have division, but they have all the other operations: addition, subtraction. If you don't have inverses, they call it a rung. They just get rid of the I. So the I does kind of stand for inverses, but that's a slang that was invented later, not from the original meaning of ring. No, I don't know but the idea is if you do a category switch from rings into groups, or groups are basically permutations of things. Well, groups are sets, and they have an operation of addition and an identity, but what they don't have is the equivalent of the multiplication operation.
Why don't groups have multiplication?
Well, groups are actually described as either having an additive structure or a multiplicative structure, but the idea is that if you take this identity and this operation and you convert it into group mode, this really becomes your multiplication in the group identity. This becomes your multiplication operation, and this multiplication here has no correlation in the group operation. It's not exponentiation. So that property, or that structure rather, has been lost when you do a category, when there's a functor rather, that takes you from the category of rings, right, into the category of groups. It forgets some information. And if you take another functor, G, and that takes you from, let's say groups into sets, now you just have a set. You don't have any operations on the set.
Right. You only have the objects themselves.
Yeah. So let's actually, I don't know how to unshare this whiteboard. Do you know how to do it?
In where?
I'm just saying, can we go back to the chart?
So in the meeting notes itself, actually, I have them side by side.
Oh, okay, perfect. So you can just see the chart. Perfect.
Yeah, I see the chart.
So the idea is that if you look now under the dimensions on the left-hand side, you'll see what a zero category is. A zero category, by definition, is a set that has no morphisms. A one category is a set that has morphisms.
Let's see. I'm looking under category set, zero category.
Mhm.
Home. So what's the HOM? Home
Okay.
X, Y.
Yeah, so the home set is just a construction. So the home set between X and Y, or X comma Y, is equal to the set of all functions, or all maps, if you will, or just all arrows between X and Y. That's all it means. So the idea would be that if you're in a category, let's just say we're in the category of groups. So let me just explain this here. Now, in the category of groups, the objects are themselves groups. So in other words, a group is a particular set, a particular operation of multiplication, which oftentimes is just rotation, or a permutation. That's another multiplicative type operation. And then there's an inverse. Those are the three rules. Oh, and then there has to be an identity. So groups have those four properties. However, this group, the square with the actions performable on a square, that group, which is like, you know, the reflections back and forth and these reflections and that, you know what I'm saying? Like there's so many symmetries of the square. I think there's a total of like 10 or 8. I don't know what they all are. That's you know, that's a group. I forget the name of it, but that's like group 1. And then the symmetries on a triangle, that's a totally different group. That's group 2.
Mm-hmm.
You know, and then the symmetries of like a cube in 20 dimensions is another group. And like, you know, some people back in the 40s, 50s, 60s really geeked out on this stuff, and they like mapped out the periodic table of all finite simple groups. They just totally geeked out on it. And of course, there's an infinite number of ways you can construct groups, but you know, there are families of types of groups, you know, square-like groups or triangle-like groups or whatever. Sometimes a card shuffling is a group operation.
A what? Oh, card shuffling.
Card shuffling, as long as you have an inverse to a shuffle, like a memory state of like undo button.
Mm-hmm.
You know, so an inverse really just means an undo button. It doesn't necessarily mean that there's a calculable operation that takes you backwards, other than you can remember the prior state.
Mm-hmm.
Yeah. So in the case of groups, and then the morphisms are they're called group homomorphisms. In other words, when one group can be seen to be fitting inside of another group. The simplest example would be that we can see several copies of this group inside of this other group here, the cube.
Yeah.
But the key is not to think of it as the square fits inside the cube. The key is to think that
Or rather
the symmetries of the square
operations
fit within the symmetries
square.
of,
right,
yeah.
where the let's just call the operations of the cube group 3. Group 1 operations a subset of group 3.
Exactly. Group 1 operations can be, you know, fit inside of the group 3 operations. That's right. That's absolutely right. And so that means, therefore, that a group like this guy can actually be factored into subgroups, no different than numbers can be factored into prime numbers. So mathematicians figured this out in like the 1800s, and they were like, that's why they thought of it as multiplication.
Wait,
the group operation is multiplication, because it's factorable. The operations are fundamentally either they're factorable or they're prime.
When you say a group operation is factorable versus prime, so what's a factorable group operation?
Oh, so the one we just did. So if you see that the symmetries on the square fit inside of the larger set of the symmetries on the cube,
Okay.
that's a factor. Then you're basically saying that, I'll write it out here, that the cube is essentially a square to like the fourth power or something like that. In other words, yeah. But where fourth power doesn't mean timesing it by itself. It means combining the sets in some form of way, in some higher dimensional way, produces, and there's even group quotients. Like it might be this, if that makes sense. Like you can even have groups that are factored like that.
Okay, interesting.
Yeah, in other words, you could show that the cube, when you take the Cartesian product of that cube, let's just say with the triangle squared, which is really just a two-dimensional triangle, actually. So it's just a triangle. Then that somehow equals something like this. I'm not saying this is an actual group equation.
Right.
But
I get what you were saying.
These are there would be equations essentially like this. And so therefore you could also describe a ratio of groups, a conversion from one group to another.
Yes.
And,
So
those conversions from one group to another are called group homomorphisms.
But then you mentioned prime.
Oh, yeah. So if, for instance, you get some funky shape, I don't know, I'm trying to draw like a funky group shape that it's like there's a well-defined way that the objects all move around each other and all the objects can operate on each other. If this doesn't break down into any smaller or simpler group.
Oh, I see.
Yeah. Then this is
this funky object, the set of operations on this funky object cannot be deduced into other simpler, or not necessarily simpler, but it cannot be deduced as a I'm just not using the right language, I guess. But
no, you're fine. You have it. You have the concept. It's the like, for instance, the triangles, the hexagons, the subgroups of the hexagon, the triangle sort of fits into the subgroups of the hexagon. But the hexagon doesn't fit inside the triangle, but the hexagon can be kind of factored, therefore, as a triangle,
right,
combined with something else.
But this other, let's say this prime object cannot be factored into others.
Cannot be factored. No, this is like the number 7, in terms of, now granted, the number 7 is the same definition. The operation that's the group operation is called +1. So +1 is the group operation that you can perform. And the idea is that 7 cannot be factored into prior subgroups. In other words, 6 can be thought of as 2 copies of this +1 +1 +1 object. 2 copies of the 3 stone object. Whereas 7 has no such representation. Right. And so that extends to geometry, basically, in the concept of what are called groups. But groups are not rings. Groups, if you now had these things, and then there was also somehow a multiplication operation on the object, which is usually not visualized. It's described as like there's just a value or a color assigned to each point in the object, except it's a color assigned to each action. That would be like a ring. And that's way more complicated. Like that's the kind of stuff I don't even want to think about.
Yeah, you kind of lost me on that one. But
no, I don't. Yeah, I don't. It's the kind of stuff that like people get PhDs in, and I'm not one of them.
Come back to category types. So we were on 0 category was mentioned 0. So this is a set 0 category.
Yeah.
On X, Y, any pair of elements in the 1 category, which is the next cell down.
Oh, yeah. So if we, for example, were to look at so you understand that there's like literally trillions of groups we could construct, right? There's trillions of them, just like numbers. There's just insane numbers of groups. But let's just suppose that we looked at all of the different ways in which the rotations on the triangle, which are themselves, in other words, how many different ways can the rotations of the triangle be turned into the rotations of the hexagon? And I don't know the exact answer, but there's some answer, which is like a math puzzle that you can, again, you can focus on getting a PhD and like solve all these little puzzles as you go, to establish these things. But it's clear that the hexagon is not prime. So the triangle does fit into the hexagon in some bigger way. And if you can prove how many different ways you can fit the triangle into the hexagon, that would be the Hom set. The Hom set would be the set of ways you could morph the rotations on a triangle and embed them into the rotations of a hexagon.
Yeah.
I think there's 2 ways, but I don't know. Could be more.
Anyways, that all just went into explain the Hom set. Yeah.
Yes. And so the Hom set thing is a complicated thing to wrap your mind around at first glance. But the reason I did the Hom set thing is to establish what it means to descend from any level number category to a lower category. So when you're at 0 category, that's a set. You just have objects. You have no transition states between them. In the case of a category, you now are looking at how do the transitions between objects in one category match up with the transitions between objects in some other category. And a lot of times you can find a functor that says to you, ding, 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 they're the same. They behave the same, even though they're not describing the same objects. The functions are essentially the same. That happens a lot in mathematics. And so category theory organizes that. But then there's another ding, 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 which is we could find what's called a 2 category, going up a dimension. In the case of a 2 category, now, just like we had before, when there's an F and there's a G, you have to prove that the thing between them is the unique function H, right? That's what guarantees that something's a category. Now, let's suppose that you had 3 functions, F, sorry, I got to draw it elsewhere, but let's suppose you had a function F, a function G, and a function H. And that took you from, let's say, point, A, here's B.
That'll be a D, right?
Yeah, that'll be a D. I'm going to put C up here, and then we'll put D. D, it'll be D for destination. So here's the idea. If you can, and A for the origin, alpha for the origin, here's the idea. If you can prove that these 2 other, let me see if I can explain this here. If you can prove that this is basically FG, if you can prove that this guy is FGH, and you can prove that this guy, which I hear is GH, then you now have what's called a 2 category. So now when you have tetrahedrons that collapse into composition, you have a 2 category. And then if you have...
wait, hold on one second. Oh, okay. So I got confused a little bit because there's no unique function going from A to C. So AC is really should really just be A to B and then B to C, which
exactly.
is
yeah. In other words, it shows that if you ever have a tetrahedron of functions arranged in a flow chart, if it's the case that I'm going to try to highlight this here. If it's really the case that the only real path you're ever really taking is this, this, and this, then essentially you've converted every tetrahedron into a path. You've linearized a much bigger network of morphisms and functions, and you've now reduced it to a path, which is why it fits in so well as a theory mathematically, because it's just converting these giant categories into lines and just showing how many ways does the category collapse is the number of the dimension of the category. So a 2 category, these tetrahedrons collapse into just paths. In a 3 category, it's, 4-dimensional triangles that collapse and so on. And it just becomes more complex networks.
So then in using that following that paradigm, the one category is when you have the
triangle.
ABC, right? Then you have a triangle. Yeah, where
Mhm.
we're
Yes.
just at. Mhm.
Absolutely. So the categories are kind of like off on the dimension of the others, but I have to keep the naming consistent with mathematical naming. So
Mhm.
you could say an n category is going to behave like an n-1 triangle, essentially. In other words, the behavior of n-1 discrete triangles informs the behavior of the n category. They're basically the equivalent of each other, and that chart essentially rising and falling on the chart shows it.
So then going from 2 to 1, I understand that. So that's essentially it's going from the tetrahedron down to a triangle, and then a triangle going from 1 to 0. But 0, then you really don't have. You just have a point, right?
You have
don't
no more triangle metaphors to help
Right.
you, so you have to work with the Homset idea, which is that if you have a 0 category, this is a 0 category. It's just a bunch of objects.
Mm-hmm.
Okay, there's no morphisms between them. So the Homset. So here's how we create a Homset from any 2 points in the 0 category. We'll call this point X. We'll call this point Y. The Homset XY, again, is the set of all morphisms between X and Y. Now, here's the thing. Do you see any morphisms between
There
X
are
and Y?
none.
Okay, so then this returns the value of false or 0. But if X and Y that we happen to choose happen to be the same point, it produces the value true. In other words, this 1 really stands for identity, and this stands for non-identity. So there's just basically 2 possible Homsets between any 2 chosen objects in a 0 category or a set. And that's the comparative. Are they the same or are they not the same? That's true or false. So that's where logic comes from in category theory, is that it's the Homset
So
the 0 category.
This is why logic belongs to the -1 category.
Yeah. Yes.
Because in the zeros category, you just have these distinct objects. You don't have functions between them. But
logical states
by
are
figuring out the Homset, which is in the -1, you can identify whether it's true or false.
Yep. Identity or non-identity. Tautology or not tautology.
All right. Now, diving into the deep end, then when you go so when you go to -2, then what? So that'll be a Homset of the logic
of the 2 logical states, and the what's going to happen is you either have so here are the 2 states. These 2 dots.
Let's start with the new page.
Oh yeah, new page.
Can you switch back to the thinner pen, because this highlighter is making it jumble up the space.
Oh, I'm sorry. All right, let's do that.
No problem. Actually, the highlighter might be easier for whoever's going to watch this later to see. I think I'm going to send this to Curt. He will have a blast out of it.
Yeah, have fun with it. Have fun with it. And I like this the best pen personally. I like to write and zoom with that thickness. So okay, so then the idea would be that you now have these 2 states, which I hear mathematicians call true and false, but I think that's erroneous. I think they're actually the states of just, is there an identity?
Right.
Or is there not an identity?
In the chart, you wrote true equals to isomorphic. Do you mean
exactly
isomorphic and identity being the same?
Pretty much, yeah. When we say that something is isomorphic,
I guess isomorphic is a more apt description, in that you really cannot distinguish A from B.
That's right.
Hence it's isomorphic.
Yeah, I'm just giving like the ISO. This is not for you, Francis. This is if anyone else is watching, just so that you see the ISO prefix in context. It just means same. So same. Same somehow. And then nah. They're different. And my claim is that at the root, true is just the and operator. In other words, that there's an overlap, and this is the
XOR, exclusive OR.
distinct. This is basically just saying they're distinct, and this is saying that they're the same. And what the Hom set is going to do in this final category is it's going to choose a pair of objects. So the Hom set chooses a pair of objects from the category and then compares them and sees if same. And so that's what the Hom set does. And so if we have the category that we call identity or true, there's an object. In the category of false, though, there's nothing there. There's nothing there. It's empty. It's the empty set. In the case of false or no identity.
Mm-hmm.
And by no identity, we mean there's no morphism, because an identity is a morphism. That's important for technical purposes. So a self-reference is still a morphism. So only in this category here can we take a Hom set. In this category, we can't do it. Or in that object, we can't take in that category, we can't take a Hom set. So therefore, the only -2 category is this true or just identity, which is essentially what category theory is all about. Category theory revolves around identification. How do different structures identify? What are identical structures to one another? That's what category theory is, using that triangle composition proof method to show that there exists a functor between type A of object and type B of object. And, rotation matrices in linear algebra behaves the same, as the SO3 group operations.
I think by the time we get to -2 category, we're at the, for lack of better words, we're at the origin of category theory. You cannot do a Hom set on this thing any further.
What happens is that a -3 category is the same as a -2 category. So it's just etc. There's no additional, it just keeps looping. The Hom set just keeps, because the Hom set always contains the one element known as true. And so
you've already gone to the kernel of truth. In this case, there you can't get any, you can't go any further.
No further gains from disambiguating using the Hom set concept.
Right.
Completely. Yeah. So I think you get it now why there are, indeed like those, -2 categories. And so the question is there a -1 and -2 dimensional state for the others? And, empty space is pretty clearly established amongst discrete mathematicians.
So I'm looking at the far left column, continuous space. You have a point which is a zero-dimensional square or zero-dimensional circle, whatever you want to call it, but it has no area.
Yeah.
It's just infinitely small point, basically.
Yeah. I'm just grabbing something.
Yeah.
Sorry.
No problems. And
I'm converting a little bit of caffeine into theorems here because it's still early afternoon for me. Early enough.
An empty space.
I'm watching my son tonight, so I got
background, a -1 dimensional square. So explain. So, okay, so you no longer have a point. It's just okay. Yeah. So that's nothing. And of course, from when it's already empty space, in essence, a blank piece of paper. If you drop down another dimension, it's inoperable.
The point acts as a container of some amount of empty space. Now, I can't tell you how much it is. We could say it's a Planck volume or something. It doesn't matter though.
I thought the point is an infinite. Well, this is why continuous space is so screwy,
No,
right?
we're no longer in continuous space. We're in discrete space.
Oh, okay, you're in okay, yeah. Discrete
Yeah.
space, yes. It's no longer infinitely small. Instead, it has some area.
It could
It's
be.
just
It could be.
the smallest, whatever the smallest area that you can realistically measure based on your instrumentation.
Yeah, and we could also just say it's indeterminate. We don't actually know the size, but it's of some size.
Mm-hmm.
And it's just, as of right now, we know that it just acts as a container of some size. So it's not a cardinal number. It's there's gonna be an ordinal logic or ordinal progression of different size states, discrete numbers, discrete, rational numbers to a highest, to, like you said, to a lowest resolution, and because it occupies some size.
And then when you move from there
So let's say,
to
suppose you have 2 points. If you have a pair of points, the idea is that you can define some kind of interior or path, either one, between those 2 points. And this is where graph theory comes in discrete.
so when you have 2 points, are we still in the row 0 dimension under discrete space, or have we moved?
Oh, I'm sorry. This is 0 dimension. This is 1 dimension. Because because
now we have a line.
The idea is that, the idea is that the 1 dimension is created by allowing there either to be an interior between 2 points or a path, one or the other.
Right.
And so the question is, for the -1 dimension.
So sorry to nitpick, but I'm looking at the picture, the table you sent me. Under 1-dimensional discrete space, you put down a 1-dimensional triangle. Well, it's not really a triangle, isn't it?
Well, there's a math convention. Yeah, thank you for that. I appreciate it. No, that's really good. I'm glad you mentioned that. So it turns out that again, this isn't, I'm referencing this all from the math perspective.
Mm-hmm.
So for math, this is called the 1 simplex, but it really just, for the layman, I teach it as the 1-dimensional triangle. And the 1 simplex is simply, what makes something a triangle is that there are 3 sides. Okay, and the 3 sides loop. Meaning that a prior point is returned to after the iteration occurs. Well, in the case of a 1-dimensional triangle, it's just boom, boom.
You've collapsed.
Exactly. So you've collapsed the triangle because the movement of those 3 movements in the path creates a looping, essentially.
I see.
And also the 1-dimensional square and the 1-dimensional sphere follow from each their own separate definition. They all, as a degenerate form, become a line segment.
Right.
Actually, a sphere is different. A sphere is different. A sphere is actually from the interval from 0 to 1 and 0 to -1, because a sphere requires you. This is actually the 1-dimensional sphere.
You mean assuming what 0 is the center of the pervasive sphere, and then you just rotate it so that you only see a line. So when it travels along the sphere, it's actually doing this.
Exactly. Yep. Mm-hmm. Oh, hold on 1 second. For some reason, I can't see you now.
I can see you just fine.
Okay, darn it. There's something just on my screen. It's on my arrangement of my screen. I'm just deleting the other windows to see if it's there.
If you're in a browser, there should be a Meet window. You can in fact find it by doing search tabs.
Oh, insert tabs. All right, let's see.
Yeah, so if you're using Chrome or Brave or whatever, there's now right next to the 3 buttons that shrinks or closes the window, there should be a down arrow, a down triangle of some sorts. And you just click on that or use the shortcut key Control-Shift-A, and it'll search tabs, and you just look for that Google meeting.
Okay. Oh wait, I don't. Let me see. I don't see that triangle. I don't see that triangle.
What browser are you using? Are you on Mac?
I'm on.
Actually, you're on Mac.
I'm on Brave. Yeah.
Wait, if you're on Brave, then it should be there. Or try Control Control Shift A.
Okay, I'll try that. That didn't work. That just brought up like Brave bookmarks. But I'll try this in Option Shift A.
Maybe on the Mac it's a little different.
Cool. Let's see. Were you describing a circle rotating into a straight line?
Right. So if you imagine 2D, right, you have a circle, but then if you just turn it on the side, then you're really looking at a line. And then when you traverse along that circle, it's one dimensional. You're looking at this.
Mm-hmm. Yeah, which I can't see, unfortunately, but sorry. Anyways,
No worries.
But I can go through all the whiteboards. Can we actually? Is it possible for you as host to like cancel the save the whiteboards and then like cancel them so that I can just? It might allow me to see you again on the window.
What do you mean?
Oh, I mean, I'm only allowed to just see the whiteboards on my browser. So I'm wondering if there's a way that they can be disabled. I'm thinking in terms
are
of
you still
the way
in the Google? Are you still in the Google Meet window?
Yeah, I'm in Google Meet. I'm on
I'm
a browser on Google Meet. I'm
I'm
not used to it.
Presenting. So if I stop presenting, can you now see me? Does that change your screen at all?
I'm sorry, I can't hear because of a rainstorm. Let me just see if I can fix my audio. You might want to pause the recording.
Okay.
Yeah, pause the recording for a second, just because I can't figure this part out, and I don't want to waste anybody's time.